Welcome. This is another Khan Academy support video. We're going to be taking a look at the fourth assignment this week called Linear Equation Word Problems, Graphs. The last two Khan Academy assignments this week are going to become more challenging because they're going to be word problems. The y-axis and the x-axis on these graphs are now going to have meaning, and you're going to have to really interpret these graphs or make sense of word problems to work through these. Our work on slope and y-intercept for these linear relationships remains very important. What we're going to find on this fourth assignment here, and I got to cut out a few notes, sorry to have a mess at the beginning, but what we're going to find on this fourth assignment is that they're going to give you linear graphs, and the big challenge or the big key is going to be you need to kind of interpret the story being told by that linear graph. And if you can understand the story being told by the linear graph between the word problem's description, the written sentence here, and the data that's shown on the graph, then answering whatever question they ask about that story is going to be pretty easy. My approach for these word problems, and you're going to see me take this approach, is to read through the description of the word problem, kind of make sense of the story told by the graph, then I look at what question they ask, and based on that question I then go dig back into the data in the story to figure out the answer. So any of these word problems, first kind of just read through it, make sense of what story is being told by the sentences in the graph, and then focus on the question and what data you need to pull out of that story to answer the question. So here we're told that while exploring a volcano, Zane heard some rumbling, so he decided to climb up out of there as quickly as he could. Zane's elevation relative to the edge of the inside of the volcano in meters as a function of time is graphed. The second sentence is a little choppy, but what they're saying, they're describing the data or the information on the graph. They're saying the graph is showing us Zane's elevation, that's his height, compared to the amount of time he's been in that volcano. So Zane's in this volcano, he starts climbing out, and we see here this blue line's moving up because Zane is climbing out of that volcano. Over time, his elevation is going up because he's climbing out of the bottom of the volcano. The question asks us, how fast or how quickly did Zane climb? And we see a bunch of answers in meters per second here. 7 over 5 meters per second, 5 over 7, 35, and 25. So immediately I start thinking whenever they ask about speed or how quickly somebody moves and it's a linear graph, I know that slope really describes the speed or the rate of change for the relationship. So if they're asking me how quickly did Zane climb, they're really going to ask me what is the slope for this graph. If I could measure the slope, telling how quickly Zane climbed should not be difficult. So recall slope is rise over run, and I need to go and ultimately find 2 points on this graph to measure how much is he rising, his elevation changing, compared to the run. How many seconds is it taking him to rise? Our key again will be to find 2 good data points, just like you did with all those times you measured slope for linear graphs. I see this data point right here that I'm going to put in red, right at the negative 25. That's his starting point. That's a great data point to use. And as I follow this blue line, I'm looking for a nice corner of a grid box. I see one right here, but that's kind of at decimals, between 15 and 20, between 10 and 15. So that's not a bad point, but I'm going to keep looking. And I see by the end, when Zane finishes up, this is right exactly on the 35 second mark, or the 35 mark for X. So I'm going to go ahead and ignore this middle data point, which you could have used, and I think these, to me at least, are 2 of the easiest data points to use to measure Zane's speed. I'm going to measure the rise. He starts at negative 25 meters, and then he starts climbing up. And I see here he has to climb all the way up to 0 meters, because the other data point I picked happened to be at the end when he's at the top of the volcano again. So he climbs up from 25, or negative 25 meters, all the way up to the 0 mark. And that tells me that Zane there, he just gained plus 25. I'm going to put the M to stand for meters. So Zane gains 25 meters. And I want to measure the run now, the sideways movement. How long it took Zane to go up by those 25 meters. So I'm traveling to the right, I'm running to the right. It starts at 0, right at the origin. And now I'm all the way over here at the 35 second mark. So to get from 0 to 35, I know he must have traveled 25 meters, and it took him 35 seconds to do so. So Zane scrambles up 25 meters. It takes him 35 seconds to do that. And if I do some division, if I do 25 meters over 35 seconds, I'm going to go ahead and set that ratio up down here now. Then I can go ahead and simplify that 25 meters every 35 seconds to try to find an answer. I could go to Google, put that into a calculator, but what's going to happen when I do 25 over 35, it's going to give me a decimal. And it turns out for this problem, none of my answers are in decimals. I see that they're all kind of fractions. So I want to take a look here now and say, which of these lines up with 25 per every 25 meters every 35 seconds? And I see these both are factors of 5. I can divide them both by 5, and that would get me down to 5 meters every 7 seconds. 25 meters in 35 seconds can be simplified to 5 meters every 7 seconds. And that's how I know that B is the correct answer here. I'm going to keep moving to the next question. As you see, these are a little involved. It's going to take a bit longer now that they're real-world word problems. But try to make sense of the context or the sentences in the graph and what scenario or story they tell you. And once you make sense of that story, then hopefully the question makes sense and you can dig into the data that you need. For our next problem, we're told that Sean is drinking a slushie as quickly as he can. And we're told the amount of slushie left in the cup in millimeters as a function of time in seconds is graphed. A complicated or messy sentence where they're really just saying, hey, this graph is comparing on the y-axis how much slushie is left in Sean's cup and how much time it takes, and you see Sean is drinking his slushie and he's trying to drink it as quickly as he can, so it's going down pretty quickly. The question that they ask us about this whole scenario, they say, how much slushie did Sean drink every 5 seconds? And we see some of our answer choices here are all in millimeters. So if they're asking me how much slushie does Sean drink every 5 seconds, I know they're really asking me about the speed of his slushie drinking. Let me get the notes from last problem out of the way. And if they're asking me about the speed or how quickly he's drinking slushie every 5 seconds, I know if I find slope, that'll tell me his slushie speed per second, and that can help me answer this question. So again, really, I'm going to underline or circle that question here in a red color, because ultimately they're asking us here about slope, and that's why I'm putting it in red when they're asking us how quickly or how fast he drinks the slushie. To measure slope, again, this should become a common refrain. To measure slope, I need 2 data points on the graph to compare the rise, the y change, or the slushie drinking, to the run, or in this case, how much time it takes him to drink that amount of slushie. I see a beautiful data point right here at the y-intercept. If I see a y-intercept that's clearly on an easy-to-read data point, like this one that's at 600, I think it's an awesome data point to use in measuring your slope. So I'm going to use that data point. And I also happen to see, you're not always going to have a nice x-intercept, you don't always have to use it, but when I see a nice clean x-intercept here, right at the 75-second mark, there's no slushie left, I think that's a great easy data point to use to measure our slope. A bunch of other data points I probably could have found in the middle. This is going to make my ratio a little larger, and it's going to need to be simplified, but they're easy data points to work with and see, I think. So this tells me, by the 75-second mark he's finished, it tells me, ultimately, I could draw out a whole big rise over run, and we'll do that quickly. But that's telling me if we start out with a y-intercept at 600 millimeters, and the x-intercept when he's done drinking the slushie is down at 75 seconds, it tells me, hey, it took this guy, I think Sean was the name of our friend, it took Sean 75 seconds to drink those 600 millimeters. So I'm going to write negative 600 millimeters. Oh. And that's how much slushie he just drank. And the time that it took him to drink that slushie was 75 seconds. I'm going to abbreviate that to 75 seconds. So if it took him 75 seconds to drink 600 millimeters of slushie, we could simplify this to a unit rate, the exact slope. And then that ultimately will help us work out how much every 5 seconds. So 2 options here. I'm going to actually do this the more efficient way. Option 1, you could switch this to every 1 second. and then you could multiply by 5 to figure out how many millimeters every 5 seconds. I'm going to make my life a little bit easier, or from 7th grade you may recall this, I could set up a proportional relationship. If he's drinking 600 millimeters every 75 seconds, the word problem is asking us how much is he drinking every 5 seconds. So we don't know that quite yet, but we have this proportional relationship. There's a couple ways to solve that. I could cross multiply, but to me, I just know to get from 75 seconds to 5 seconds, I know 5 times 15 is 75, so I'm going to divide both of these by 15. Divide both of them by 15. Because if I divide both by 15, that can work me from 75 down to 15. And it turns out that 600, if I do 600 divided by 15, that gives me 40. So that tells me 40 millimeters every 5 seconds. Another way around, you could have done that, you could have just done 600 divided by 75, and that would have got you to your unit rate. 600 divided by 75 tells us the real slope here is ultimately 8 millimeters. So if I just did the division, 8 millimeters every 1 second, and 8 millimeters every 1 second when I multiply by 5 tells me 40 millimeters every 5 seconds. So a couple ways that I could have taken this slope of 600 over 75 and figured out how much every 5 seconds. Again, there's my work, 40 millimeters every 5 seconds, and I see that it lines up with answer choice C. I'm going to clean some of this nonsense up before we go to the next problem. As you see, these are in-depth problems. Please don't be intimidated. Do your best at reading, making sense of them, and also please, please feel free to reach out to me if you need any help. And unfortunately, I just lost a bunch. Bear with me 1 second. All right, next question. We're going to show one more example, and then please, if you're getting different graphs and you're struggling to make sense of them still, you can feel free to send me an email. We can jump on Zoom and I'll help you out. So I'm going to show one more here. We'll read through the problem to make sense of it first as always, then focus on the question and dig back into the details. So we're told that Archimedes drained the water in his tub. The amount of water left in the tub as a function of time is graphed. So here they're telling us in that second sentence, water is on the y-axis, time in minutes is on the x-axis, and they're measuring the relationship between how much water is in Archimedes' tub over time. We're told that Archimedes was draining that tub, and that's why we see the blue line moving down, because Archimedes is losing water out of that tub over time until it's all the way emptied and drained at the end here. The question asks us how much water was initially in the tub. And here, I should recognize I'm going to switch my color to green, because if they're asking us how much water was initially in the tub, they're asking about the y-intercept. Where does this relationship begin? And when I look on this graph, I'm going to put a nice green dot right on the y-intercept, and we see the y-intercept is right at 360. And what that's telling us, this graph is literally stating at the 0-minute mark, there's 360 liters of water. That's what this data point right here is telling me. It's at 0 minutes, 360 liters of water. We like the y-intercept because it tells us a key part of the story. In this case, how much water was initially in the tub. You may have recalled we called the y-intercept an initial value, and we'll continue to do so. That's because it describes to you the starting or initial point. I hope those videos were helpful. If they are not, I do believe this is a tough assignment. So please feel free to send me an email, and I'm happy to jump onto Zoom and work with you, and we can kind of talk through them and make more sense of some of these challenging word problems.